Okay, so yesterday we talked about control more from a theoretical and high-level standpoint in terms of how controls fits into robotics and why we need controllers in order to implement semi-autonomous and autonomous capabilities on robots. We went through the cruise control example just as a motivator and to give it something a little less abstract. Just to recap real quick, what are the two main branches of control that we talked about right at the beginning? Yes? Open and closed loop. Do you want to take a crack at what the difference is?
When it's closed, it has feedback loops.
Yes.
Sort of an open, more simple way.
Right.
There's input, output, which is U and Y, and which in our case is the vehicle.
Yes, that's right. So in your case, the plant would be the vehicle, the thing that's under control. And like your colleague said, in the case of closed loop, you have something called feedback, where you're taking a measurement of the output, right, an estimate, and you're feeding that back into the controller. In the case of open loop, you're somewhat blind, which is why I particularly like the example of driving cruise control with my eyes closed, because that's what open loop control is you're not getting that feedback information. So if you're off, there's no way for the controller to know that. We talked about some cases where sometimes it's actually advantageous to do open loop control over closed loop control. However, when people talk about control, it's almost understood implicitly that we're talking about closed loop control. Okay, so today what I want to do is, right off the bat, I want to just talk a little bit more about some of the stuff that we've worked on at JPL, and particularly stuff that I worked on. Because like I was saying yesterday, one of the reasons I'm here is to be a resource for you guys, to answer your questions, to tell you about what it's like to work in the field of robotics right now. Again, you guys are the next generation of robotics engineers. So you'll be, when you're 28 like me, you'll be up here talking about control systems and robotics, and you'll have a different perspective than I did.
Can I interrupt?
Absolutely. Oh, okay.
Does anybody know, just looking around, who's not here before I call by names? No? Okay. Mariam?
Here.
Jacqueline?
Here.
Spencer?
Here.
Matthew?
Here.
Raj?
Here.
Darwin?
Here.
Chris?
Yep.
Manny?
Here.
Raphael?
Here.
Will?
Here.
Jose?
Here.
Michael Bresco?
Here.
Syed?
Here.
Joshua?
Here.
Esther Ickes?
Here.
Eric Yang?
Here.
James Johnson?
Here.
Jonathan Kagoo? I'm gonna mess this name up. I'll just say last name, Julia.
No, here.
Michelle Lee. Stephen Lansky. Okay, found it. Thank you. Thanks, Kyle.
Okay, we're good? Okay. Okay, so let's watch a video. The video I'm going to show you is of a robot at JPL called RoboSimian. This is a four-legged, so quadruped walking robot. It's called RoboSimian because it's somewhat ape-like. We designed, built, tested, and then implemented this robot in something called the DARPA Robotics Challenge. And if you haven't heard of the DARPA Robotics Challenge, I recommend reading about it if you're interested. It was a challenge where DARPA, who's a DoD agency, solicited proposals from all across the world for people to either build or buy one of DARPA's robots and then compete in a disaster response challenge, a simulated disaster environment where you wanted to send humans in, but it was too dangerous to do so. Something like Fukushima, where we could have prevented a lot of the disaster had we had the capability and technology to send robots in to do things that aren't even particularly complex for us, like turn valves. But for robots, that's a very tall order. And so DARPA made this competition to try to push the robotics community to get to the point where we could do stuff like this. So JPL entered into this competition. There were two stages, trials in 2013 and the finals in 2015. I only worked on the finals, but I was the controls lead for this robot for the finals, as well as the lead operator. The thing is not fully autonomous, so we're sending it high-level instruction because DARPA was throttling our communication with the robot while we were operating, and we were operating remotely. So we were in a bunker, like a quarter-mile away, cut off from the outside world. This robot was operating on a course in front of thousands of people, and we had very limited connection to the robot. So we couldn't joystick it around, just like the example of Mars that we were talking about yesterday. This was to try to push autonomy onto the robot. So here's what a high-speed time lapse of this looks like. We'll go take a look. I'll talk while it's going. So there were 8 tasks in this competition, and you had an hour to complete them. At least was the goal. The first task was to get to the disaster site. So the robot had to be in the vehicle, and you had to drive it to the disaster site 200 meters away. That got you 1 point. Then you had to get out of the vehicle. This was a second point. So this is our 28 degree of freedom 4-limb quadruped. So it can walk, but then also it can sit on rear wheels and drive. Why walk if you can drive? Then opening the door was a third point, a third task. You had to go in, find a valve, open the valve. The next task, this was a surprise task. They didn't tell us what it was ahead of time until right before. It was to flip that electrical switch. This by far was the hardest manipulation task. It was to pick up a cordless D-wall drill and cut a hole in drywall with it. This is hard to do if you're a human. That drill is not designed to cut sideways. So that was the 5th task. The 6th was to either clear this rubble or walk over the terrain. For us, it was really easy to just drive through it. That was the 7th task. The last task was to walk up this set of stairs. This is the only thing that RoboSimian didn't do that day. And what it came down to for us, why we didn't walk up those stairs, was testing time. So you'll learn, and it sounds like maybe you've already started to learn a little bit, what it's like to work with real hardware and real software. It's not necessarily easy. You may have an idea in your head of what you want to implement, and it's something very simple. But the reality of when you get it on the hardware is very different. Things don't work the way you expected, and now you have to debug. And it's that debugging process that costs so much time. So when we were using this robot, we had this robot fully functional 6 weeks before the competition, the full thing. Not a lot of time, but you might think, oh, it's only 8 tasks. Like, you should be able to just get through all of them. No. Since the stairs were the last task, we kicked it all the way out to the end and said, we're not going to work on those until we get to the, unless we actually get there. And we didn't. So we couldn't walk up the stairs. So that's just an example of one of the more advanced robots that we're working on right now. And what's very interesting about this challenge is if now, so a lot of people competed with humanoid robots. If you look up videos by a company called like Boston Dynamics, you'll see robots way advanced beyond this. But the thing is, that advancement happened because of this challenge. This challenge pushed the community to get to that point where we could build much more advanced robots. So just a little historical thing that very much had an impact in the robotics community and will impact you either, even if indirectly. The other reason I want to mention this is, yesterday, what was the control technique we talked about that I said is the most widely used in industry? PID, yeah. Do you think there's PID running on RoboSimian? Yes, absolutely. There are 28 joints on that robot. Each one has a motor in it. Each motor has something called an encoder. The encoder gives us position knowledge of the motor. And the way we control the motor to a position set point is with a PID controller. In fact, it's actually a cascaded loop of 3 PID controllers. We also do something called force control with this robot, where we have, at the end of the arm, there's a force sensor. So if I want to push against the environment with a certain amount of force, or pull down on a lever until I hit a certain amount of force, we have a PID controller for that as well. Any questions on that guy? Yes?
The DARPA challenge, do they change every year?
So the DARPA, it actually is a one event kind of thing. So the way DARPA works is they say, we're going to do this competition. And in this case, it was a 2-stage. There were a trials and a finals. But then their goal is to push the community to advance their technology and then just pick it up and run with it. And then they kind of back off. So their idea is to provide a relatively, for the advancement, small amount of funding to get everybody together and focused. And then once the community gets rolling, then they back away. So next time they'll do a different kind of competition. It won't be like this. And if you go back in time, 2004, 2005 is something called the DARPA Grand Challenge, where it was autonomous driving. And a lot of the technology that you guys are working with and the open source packages in ROS came out of that competition directly. You have something called the Hakuyo LiDAR on your vehicles, right? those used to be like hundreds of thousands of dollars. Not because they're really expensive to make, but because nobody was buying them. So manufacturing-wise, the volume was very low. So the companies had to charge a lot to make a profit. After that competition, and Google started doing autonomous driving, and then other people did, and now it's like every company in the world is working on autonomous driving, the cost has come way, way down to the point that you can buy those sensors for a course like this. It used to not be the case, not very long ago. Okay. So with that, what I want to do today is talk in more practical terms about control, particularly as it applies to your vehicle and sensor suite, and how you might implement some of the controls we talked about yesterday for the wall following case. Have you guys talked about the wall following controller at all?
Yeah.
A little bit? Okay. So I think the idea is you have your car driving along a wall, and you want to just maintain a distance from the wall so that you go in a straight line along it. So we'll talk about how we do that. Before I start, are there any lingering questions from yesterday? Okay. As always, feel free to stop me anytime along the way. All right. Let me just draw on the board here the open versus closed loop controllers, just so we always have them up there as a frame of reference. So in the case of open loop, like we talked about just a few minutes ago, the reference comes into your controller. Your controller spits out an input U to your plant, and you get some output. The output is not fed back to the controller. So if the controller is wrong about what it's trying to do, it has no knowledge of that. In the case of feedback, we have this what's called summation block. And here, I'm just going to write EST for estimation. We feed back an estimate of the output that we're trying to control, and we subtract it away from our reference to produce what? Oh, and I forgot something. What did I forget? The controller. So we get an error. The error feeds into the controller. What's different here? Well, here it's just a reference. It's where do I want to go? Here, embedded in the error term is both where do I want to go and where am I right now. That's the key distinction. Okay, this is looking better. Okay. You are tasked with the problem of you have this autonomous vehicle, and yes?
Sorry, so like with the closed loop, like with your notation, is like when you're actually coding it, is it as simple as like you subtract the estimation from the actual like R? Because like I noticed with the notation you have like a plus and minus there. So like do you just subtract the estimation from the actual R when you're inputting it to the controller to determine the error?
In most cases, yes. Certainly in the case of PID, like we're going to talk about, yes. You literally just say, like, I want to be a meter away from the wall. How far away am I from the wall right now? OK, half a meter. Then my error is half a meter. And that feeds into your controller. Yes, there are more advanced ways to do this outside the scope of this course. And there are also cases where you have what are called multiple input, multiple output systems, where you're not just trying to track the distance from the wall. Maybe you're simultaneously trying to track your speed, something like that. And so you could have this line becomes multiple outputs, and this becomes multiple references. And so then what happens here gets a little bit more complicated. Does that answer the question? OK. Anything else? OK. So like we were saying, you're tasked with the job of taking your RC vehicle, which is fitted out with sensors and software, and driving in a straight line. Why? And we're going to do that by following the wall. Why would we follow the wall? So that we can drive in a straight line. OK. So let's look at just a diagram of what that looks like. So we have your RC car. Let's say you're driving at some speed with some velocity, v. So this is like your linear speed forward. And then over here you have a wall. And what you want to do is maintain a distance from the wall. How far we are away right now, let's call that d. This is our current distance. And we want d to be equal to some value. R, right? Our reference is what we want. Another common notation in controls is once you're in the implementation side where you're talking about real values, right? Reference here could be anything. This could mean anything. Temperature of the room, speed of the car, distance, velocities, whatever. A typical notation would be to call this d desired. Your desired value for d. And then this guy is d actual. Or actually, you know what? Instead of actual, let's call it estimated. Just to hammer the point home that you have a LiDAR on the car, right? I think you guys have worked the LiDAR a bit. Someone want to explain super fast, how does that LiDAR work? Yes?
It shoots lasers and it calculates how long it takes the laser to come back. And so you don't actually know the actual exact distance, but just rather what the sensor says it is, so it's estimated.
Right, exactly. So it's estimated, yeah. You don't ever actually get to know how far away your car is from the wall. What if you had a tape measure? Could you measure it perfectly? No. Nope. And this is the thing in robotics of how do you get what's called ground truth? How do you actually know that you're doing the right thing if you can't measure it? Well, one way you do it is you put a cheap sensor on the robot and you estimate your distance with the robot. And then to see if you're at least in the ballpark, you buy a really expensive what's called metrology system, which allows you to track the vehicle and this distance from the wall and say, we're at least within 0.1 millimeters, and that's sufficient for this task. That's typically how this would go. So the idea is you're estimating d here. You don't actually know it, but you have a very highly educated guess. Okay, so the control objective is simple. What is the control objective here? Yes?
To maintain the desired distance from the wall while driving along.
While driving along the wall, right. So we want d estimate to equal d desired. That's the whole goal. Okay. So let's talk about that. In the simplest sense, right now my car is pointing to the right. And I have some distance that I am away from the wall that I'm estimating, and I have some distance that I want. Suppose right now, well, first off, what is my error term in this example? Yes?
Desired minus estimate?
Yes. Yep. The error term is d desired minus d estimate. We're feeding in d desired. We're estimating d. Compute the error term. If my error is negative, which way do I want to turn the vehicle? Yes?
To the right towards the wall.
To the right towards the wall. Do you want to explain?
Because if the error is negative, that means that the de-estimation is larger than the de-desired, so then it's further away from the wall.
That's right. Did everybody hear that? So if my error term is negative, that means that my estimated distance from the wall must be larger than what I want it to be, which means the vehicle is too far to the left, so I need to turn to the right. Before we talked about PID control yesterday, what was the other technique we talked about? Bang, bang. If I wanted to write a bang, bang controller, this is how simple it is. I would compute this, right? And I would say, if my error is less than 0, then u, which in this case is, what is my u? Let's talk about that. What is my input to my plan?
Angle of your front wheels.
Angle of the front wheels, right. So you guys, I believe that there's a ROS node you're going to talk to where you give it, you have like an Ackerman steering angle, right? So that is your U in this case. So if my error is negative, that means I want to go to the right. So then my U is just going to equal some steering angle to the right in the case of bang bang. It could be your max. So we could just call it max right. And if my error, let's just say otherwise, what is my U? Max left. Okay, pretty simple concept. So, too far away from the wall? Great. We're going to tell the car to turn as far right as it can and get closer. Eventually, the error term is going to flip signs because now we're driving towards the wall. And so now we need to turn left. And so what you'll get is this oscillatory behavior if you were to implement this where suppose this is my projection of D desired. This dotted line represents where I really want the car to be traveling. You'll find the car will get over here, and then it will do something called overshoot, meaning it's going to go past your desired position, and then you're going to turn left, and then you're going to overshoot again, then you're going to turn right, and you'll do that. For some applications, that's OK. Sometimes the oscillations are no big deal, and it's worth it. We talked about air conditioning yesterday. Doesn't need to be particularly complicated, because the rate at which the output changes, i.e. the temperature of a room when the air conditioner kicks on, is really low. So you don't get these wild oscillations in temperature when you're turning an air conditioning unit on and off. OK, but for your application, you want a little bit more. So we go to our friend PID control. And PID control will not turn as sharp as it possibly can towards the wall all the time. The idea is, as you get to your target, what should the wheels do? Yeah, start to back off, just like the throttle in the cruise control example, so that you don't have this oscillatory problem. Can you still get oscillations with the PID controller? Yes, you sure can. For those of you that implemented one, you've probably seen it, and we'll talk about that. In fact, at the end, Mike has an awesome demo where we're going to go through what this looks like on a very simplified mechanical system, what some of the responses you might see look like. Now, the thing is, the responses you'd see in the simulation versus your car, while the applications are different, the concepts are the same. Oscillatory behavior, something called instability that we're going to talk about, overshoot, undershoot. These are concepts that are universal across all systems that you may control. It doesn't matter what the application is. So what you find is time and time again after you implement a PID control, you start to get faster and faster and faster at tuning this thing because you start to get better and better at it. All right. So let's go back to PID control then. So I'm just going to write this same equation back on the board. We have Kp times E plus Ki times that integral term of our error plus Kd times this. And we didn't talk about this one at all yesterday, but we will, dE dt. Just to summarize, this guy is your reactionary term. It thinks only in the moment. It looks at your instantaneous error. Here, things start to get a little less simple. This integral term, again, is something you'll learn about in calculus. It ends up becoming really important even to understand things like physics. But for our purposes, what this integral term means is it's literally the summation of all your past errors. Every time you compute a new error when your controller updates, you add it to this summation. And this term you can use to get rid of something called what? Steady state error, where you'll find with a proportional controller only, you'll end up with something called a steady state error at the end. And steady state error, again, if I were to plot it, looks something like this. My error comes down, and then it just decays off to some fixed value, and I can't get it smaller than that. That's what can happen with a proportional term. The integral term, its job is to say, hey, wait a second, I still have an error here. I'm going to add that to my past history. When I update and take another measurement here, I have an error again, so I'm going to add that to my past history. So what's happening to this term? It's growing. It grows and grows and grows. It doesn't stop growing until what? Until the error is 0. And one of you come up and talked to me yesterday about, well, what does this end up looking like? And actually, I made an error in what I said. I said that eventually this term will go back down. It won't. The only way that this term will start to go down is what? Yes. Negative, yes. The only way for this guy to become smaller is if my error crosses and changes signs. Now I'm adding a negative error to this, and that will start to bring it back down. But again, the idea with this term, in practical purposes, is to get rid of this offset. And it does it because it penalizes steady state errors. It wants to get rid of them because it's constantly adding them up. So if it sees you're always at some non-zero value, it starts to slowly increase your input as a result. Every time, it's going to make it bigger and bigger and bigger until eventually this thing drives to 0 and you hit the steady state condition where you look more like this. Do you always need this? No. And for your purposes, you may or may not. Do you always need this? Pretty much. But I could tell you after class about an application where we only have this. But most of the time, you have this term. And in fact, this is your hardest worker. For the most part, this does the bulk of the control. This guy's designed to get rid of steady state error. OK, this term, this DEDT business. This is fancy notation in calculus, which means I'm looking at how quickly my error is changing in time. The DE means you can think of it like I'm looking at the change in my error. How much has it changed? And the DT means how much has time changed. So in essence, I'm saying, what is the rate of change of my error? This term, again, looks at just what is my error right now. This is looking at how quickly is my error changing. Does anyone know why this term in practice ends up becoming so important?
Like prevent like really like quick influxes of V.
Yes, it can. Yes. Yes.
A lot of about the momentum, so it stops basically like keep overshooting, so it like slows it down to get close to more than before.
Right. Yes. Anybody else?
Isn't it like a method of dampening?
It can provide, yes, something called damping. Yes. OK, all great answers. Yes, so remember how I said that bang bang controller oscillates? You can get that oscillatory behavior. You can get that with PID as well. In practice, this term helps get rid of those oscillations because this doesn't like to see error changing. As small as it may be, it doesn't like to see velocity. It doesn't like to see this switching back and forth. Because what this wants error to be 0. This wants, like in the moment, this wants steady state error to be 0. This term wants your error to not change. It wants the rate of change of your error to be 0. And I'll give you an example of this. Back to your car. Let's suppose again, this is our setup. My car is currently pointing to the right. So what's going to happen as the car starts to drive forward to my estimated D? It's going to what? Go down. Suppose that right now we happen to be at D desired. What's my error right now? 0. Suppose I only had a proportional controller. Does it think its job is done? Yes, that's the problem, is it thinks it's done. But the reality is my car is pointing to the right. So what's going to happen next time I update? It's going to get closer. Did this controller see that coming? No, I had no idea. It said, oh, we're done. We're at 0. Did this guy see that coming? Yes. It saw it coming because as we're moving in this line, again, what's happening to my estimated D? It's decreasing. So is it changing? Yes. That gets picked up here. So if the goal of this part in your problem is to get this distance exactly right, what is the effect of this term? What does it do to the car? What is it trying to accomplish? You've answered a lot of questions, and they're awesome, but I want to see if anybody else has a thought on this. What does it mean for my error to not be changing anymore? Yes? Straight. The car must be going straight. Right? If you think about it, the only way in which this will work is if my car is going perfectly straight. That keeps my estimate at some fixed value. And because this is fixed, this term is 0. That's the only way. So this guy trying to get you to the right distance, this guy trying to make your car straight. What if I only had this term? What would happen? Yes?
Go straight?
It would just go straight. Would it be at the right distance?
No.
No. So do you need both for your problem? Yes, you do. Yes, question?
Could it ever be that the derivative one cancels out the original the reactionary term? So like they conflict in a sense, because like if it's going straight, but like the de-estimation is greater than d desired. Would the want of being straight overtake the want to go to the desired distance?
That is an excellent question. Does everybody understand what he's asking? He's saying you have somewhat competing objectives, right? We want the car to be straight, but if the car's straight and we're way out here, does this want to allow you to change it? No, it wants you to keep going straight. But what does this want? It wants you to turn to the right. What the heck? That's where tuning comes in. That's where tuning comes in, because they have different objectives, and together they can work together really well. But there are cases where, like, this is a very clear one, where they're going to be competing. That's actually okay. Because what does that competing mean? It means that ultimately, this term says, I'm done, I'm going to apply 0, right? This term says, wait, I need to turn to the right. So the car's going to do what? Start to turn to the right. Then this guy says, whoa, 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 we need to straighten out. What that effectively does in practice, if you have the right gain set, is it makes sure that this doesn't turn your car too quickly. This penalizes you turning too fast. If this just says, I want to turn super sharp to the right, this will cancel out that in a certain sense, that it'll say, you can't turn that fast, so I'm going to give you a negative added to your positive to make this smaller than it would have been. What that means is you gain something called stability, where this isn't allowed to dominate your system. This is like a check on this guy. Always looking at, are you asking for too much here? Are you asking for too wild of a turn? And this will help offset that. Yes?
Does it also mean like the farther it is, like the more powerful KP is, but then like as it gets closer to like the desired distance, then like it starts to lessen, so then the derivative takes over, it starts to like kind of like soften the...
Yes, that is right. And so the further away you are from your objective, it's a very good point, the more aggressive the behavior of the vehicle will be. You'll see larger steering angles when you're far away, because this term is much bigger. And this one doesn't care how far you are away, it just cares how much you're turning. Yes?
So with the oscillation with the PID controller come from the integral term even taking this particular example, even if the error becomes 0, the integral term is always going to have a value greater than 0 because in the past it had an error.
So, okay, so if we throw the integrator back in, yes, the question is that what's causing the oscillations? The answer is it can cause oscillations because of what you're describing. But back to the cruise control example, if I'm driving a car and I hit my target of 70 miles an hour and I let my foot off the gas, what happens to the car? It slows down. Why does it slow down? Because there's external things acting on my vehicle. Friction, well, friction somewhat internal, but then there's rolling resistance of the wheels, there's aerodynamic drag. What that means is I always need my foot on the gas at least a little bit. The Ki term is what provides that always because it's been summing all along. So you end up with a value where even when I hit my error equals 0, the Ki term is still applying an input. And so it can cause oscillations because it can cause you to overshoot, but the idea is that what it really should be doing is just making sure you're driving that error down to 0 because it is what is going to make it so my foot stays on the gas a little bit. Does that make sense? Okay. Yes.
But in the case of a car, wouldn't it just always make it turn or have a certain steering angle?
And make it always have a certain steering angle.
Steering angle.
Yes.
So then if it's always that integral term, it always will.
Right, that's a great question. Okay, so the question is, if you have the integrator, doesn't that mean your car is always going to steer, like, say we started to the left, the integrator is going to start to add, and it's going to want us to turn to the right, and then when we get to our target, it still wants us to turn to the right, right? That is where you can get oscillations. So what happens is then you do something called overshoot, where again you drive past your desired value. The integrator then starts to add negative values, and starts to go down, then it hits 0, then it becomes negative actually, and the car will start to turn back to the left. So you may get some sort of oscillation. But here's the other thing about real hardware that's different from like a simulator, a perfect model, is if I took your RC, or you took your RC car and you told it to drive straight, and you gave it 0 as a steering input, do you think it would actually drive straight? No, why not? The wheels aren't exactly the same size. There's some sort of like hardware calibration that needs to take place, right? If you kept driving it, even if you had it super well calibrated, like, man, you knew the wheel size so well, you totally trimmed this thing with like your little controller to make it so that it drove straight. If you drove it for a mile, would it eventually deviate from a straight line? Yes, absolutely. And so in that sense, even in the example of turning, most likely, you're going to find to get that car to drive straight, you actually need a little bit of a bias in your input. It's probably not the case that 0 degrees means the car drives perfectly straight. And that's where the integrator can come in to help you. But again, it's not necessarily a requirement. It all comes down to how important is it to you to get rid of this steady state error. And then you have to ask the question, well, how much steady state error is it going to be if I only implement a proportional term and maybe a damping term? And that's where tuning comes in, because oftentimes the only way to know that, or the fastest way to get to that answer is to just implement it on your hardware and see what happens. Sometimes that's not an acceptable solution. But in this case, you guys have the hardware at your disposal, so it's OK to do so. Yes? Yes. Yes, so when we're talking about tuning and gains, what we're talking about are these 3, and I love that term, weights. They're how much do you care about instantaneous error, how much do I care about my integrated error, and how much do I care about how quickly my error is changing. And that's what makes PID so tricky from an academic standpoint, is it's hard to know what these values should be. And that leads me perfectly into the next thing I wanted to discuss, unless there's any lingering questions, which is some high-level tips on how to tune this. And then Mike actually has, like I said, a nice simulation that we're going to go through so you can see what some of the behaviors we're talking about are. And then you will implement it on your car, and you'll be able to see what we were talking about. But any last questions on anything we've talked about so far? OK. Before we talk about gains, there's one last thing I want to talk about, actually, which is, in practice, this term is a pain. Does anybody know why? I want to estimate how quickly my error is changing, right? Suppose I took a simple approach to that, where I say, okay, I want to know how quickly my error is changing. Well, what's my error right now? Okay, I'm going to save that value. Next time I update, I'm going to say, now what's my error? What could I do? I could subtract those, right? So that's the difference in my error, and divide it by how much time has gone by. Does anybody know, and this is not something you would get to till a college level controls course, and even then people don't know the answer, so I don't expect you to, but does anybody happen to know what the problem with that approach is? Yes?
It can be computationally intensive, so like you have to like keep on refreshing and like deleting and adding terms.
It's true, you do need like a static variable to carry around so you can remember that, but that's actually not the issue I'm talking about. Okay, the real issue is, suppose I have a sensor giving me some value. I don't care what it is. It's something that I'm using in my controller. Maybe my sensor is a voltage and it looks something like this, okay? So when I'm saying at this time t, I'm going to grab its rate of change or derivative. What I'm really saying is I want to grab its slope right here. And I'm approximating this slope by saying I'm going to take this point and I'm going to take this point and I'm going to subtract them, get that delta, and then I'm going to look at the time delta. So at my t minus 1 to t, how much time's gone by, and how much has my value changed, and that gives me a linear slope, and that's my estimate here. Here's the problem. If I zoom in on this sensor, it's analog. Analog sensors have something called noise, and you can't escape it. It's everywhere. So if I really zoomed in on this, here's what it really looks like. That is what a real sensor output looks like when you zoom in on it. There's something called high frequency noise. The high frequency noise ends up making this kind of computation, while tractable, very inaccurate. Because as I estimate the slope, what I really care about is like that value. That's like the real change that I'm interested in. But on top of it, I have all this stuff, which comes from all kinds of electromagnetic interference. It comes from quantization on the motherboard. There's all kinds of sources for why you end up getting noise. But this means that as I do this estimate, I get these wildly different slopes. And it's almost unusable when I put it into my controller. So there are all kinds of tricks about how to get around this, where you can apply something called a low-pass filter to try to eliminate that high-frequency noise. That is other issues. But there's something in particular on your RC car that Ken, who's very, very clever, by the way, thought of that I did not, which you can use to estimate this value instead. So let's go back to that. And I want to mention this really quick because it's important. Then we'll talk about gain tuning. OK, my car's driving along. I have some estimate of D that comes from what? What sensor are we using? The laser, right? So your laser is shooting out these beams. You could say something like, I'm going to take the beam with like the shortest distance and assume that that's my D to the wall. OK. So you could take your sensor value. You could do what I'm describing here, where you say, I'm going to take the value now. I'm going to compare it to what it was before, and then I'm going to look at the difference. But you're going to run into that noise issue. I guarantee it. So the clever thing that Ken thought of is, do we know this? V. Do we know how fast we're going? Yes. Do I know, let me redraw this. OK, so I got some velocity V. I have some distance d, and I have a wall over here. Do I know this angle, theta? Yes. Because I know which beam is the one that was shortest, so I can estimate from that what the orientation of my vehicle is. And I know this velocity. So let me get rid of d. I know how quickly I'm driving towards the wall, and I know what angle I'm at with respect to the wall. So it turns out that you can use this velocity and some simple trig to figure out what this value is, which effectively is your dE dt estimated. Does that make sense? This is a cleaner way to get this estimate than it is to use that sensor. Is this going to be a perfect estimate? No, it's not. That's okay. It's better than than doing what I'm describing here. So this kind of thinking is really, really crucial in engineering, because this isn't stuff that you learn in college. No one tells you, like, oh, if you have an autonomous car and you're driving along the wall, instead of using this kind of derivative or estimation, use your forward velocity and blah, blah, blah. No, like, this is on the engineer who's implementing the controller to come up with, or someone to come up with. And that's what's so cool. It makes it so interesting. Okay, so really fast, I want to mention my cookbook recipe for how to tune a gain set. Again, these 3 weights, and we'll talk about what this looks like in a simulation. All right, so you code up your controller, your PID controller. You have your estimated D. Maybe you've measured it with a tape measure to make sure it seems reasonable. You have your estimated rate of change of E. That's all working, and now you want to get this controller actually moving the vehicle. The first step that I always take with the PID controller is start with a low KP and then increase it. How low? I have no idea. Totally application dependent. You just start bumping up this value until you start to see your system respond. You'll start to see, as you're driving along, you'll start to see your car start to turn. You stop when too aggressive. What do I mean by that? Again, KP is kind of greedy. It only thinks in the moment. What does too aggressive look like in a controller? It looks like oscillations. So it'll look like something like this. If this is my error term, you'll see it come down. We'll get something called overshoot, and it will do this. If my KP is too high, I get something called instability, where you'll see wild oscillations that shoot off to infinity eventually. That's how you break hardware. I've been there. Okay, so you stop when it gets too aggressive. Then bring in KD. What does KD do? Again, it wants your car to go straight. It hates seeing stuff like that. So you bump up your KP till you start to see the car respond, bump it up a little bit more till maybe you get a little bit of oscillation. Then you bring in your KD term and same thing, start to bump it up until you see these oscillations go away, or at least decrease to an acceptable level. You'll never get rid of them completely. And then 3, if I'm going to abbreviate here because I'm running out of time, if your steady state, SS, error is too high, then start bringing in the integral term a little bit at a time, and you'll see this effect. You'll see this steady state error start to drop, drop, drop. If you bring in KI too much, you'll go back to this instability. So this is where the intuition starts to get built. 2 other ways to come up with gains. One is called Ziegler-Nichols tuning. It was invented in like the 60s. It was a more rigorous approach to coming up with these experimentally. It doesn't work. The second is something called model-based design, where you have a physics model of your vehicle, and based on the physics model, you can actually prescribe what you want this response to be and mathematically compute what those 3 gains are. That's something you learn in control theory. Does it work? It can work if you have a very good model of your vehicle, and that is very difficult to do. Yes?
Everyone's saying that, like, if it's already working fine for the first 2, we don't need...
Great point. Yes. If it's already working fine for these 2, don't bring this in. The other thing about that is don't bring this in until these are working. This will just make your life more painful. There are applications where you don't want a D, you only want a PI. That's not your guys' application. We can talk about those offline if you're interested. But yeah, that's the basic idea. Yes?
So you
want to either like get rid of not all the oscillation, but just have like a little, like reduce the oscillation a lot, or you just want to have just steady state error?
Right, great question. So you can't fully ever eliminate the oscillation, but you may be able to eliminate it enough to the point where it's not perceptible by you. And it's really, I don't know, maybe your course instructors have a specification of what they want your controller to do, or maybe it's up to you to say, this is good enough. The real question about control that always comes back to is, what are we trying to do? Are we trying to follow the wall and that's it? Or is there something that we're going to build on top of? Is this something we're going to build on top of? And I guarantee you that's the case. So then the real question is, what are we trying to do next in order to answer what does the controller need to do now? I think one more question, and then let's jump to Mike's. You want to set up, and then, all right, cool.
Why is the noise on the sensor specifically a problem for the derivative and not a problem for the integrator or?
Okay, good question. Okay, so your colleague's question is, this noise here, why isn't this a problem for here? Okay, it is a problem, but it's much, much less of a problem. Because what happens is, you can imagine this is my signal, right? And this is, within this band here, like I might be anywhere inside this band, and there is noise in here, but at least it's pretty close to what I care about, which is this value here. When I start to take the differences of these values, if I were to plot that, it blows up to something like this, meaning the derivative term amplifies the effect of the noise. It is much more dampened in the KP term than it is in the derivative term. In the derivative term, this noise becomes dominant over what the true signal that you care about is. Does that make sense? But you will get a little bit of noise in there, and you can lead to instability due to noise. You can have sensors which are introducing noise, and it can be a problem.
All right, guys, so what I have, I'm going to show you guys is a quick little demo on basically a mass that you can move left and right using a controller. So how many you guys all taken physics? Raise your hand. Yes, more or less, some of you guys. OK, so essentially what I'm going to show you here is we talked yesterday about this bang bang controller. So you see we have this block. It's kind of small. Can you guys all see that? Can't make it any bigger, but essentially you have this block here that when you hit go, you give it a reference command, which I can control right here, saying, OK, I want this block to go to 1. And my control input is basically I can just exert a force left or right on that block. And you're going to see that force in that control effort in the middle there. You'll see that a little purple line showing right or left which way you're exerting a force on the block. So who wants to predict what a bang bang controller is going to do this system? Oscillate. All right, so ready? I'm going to hit start simulation. And the block's going to go back and forth. Is that what you guys expect or what? And so when the simulation finishes, you can see what's called the step response. So what we essentially did here was we told the block to go from 0 to 1, and then this is the system's response to that input. See, so we see our reference command, the green line there, and the block just going up and down continuously, not slowing down. You want to interject or?
No, that's great. So this is exactly what we're talking about, right? That you get oscillations, and then he's plotting that with respect to time. Like we said, bang bang control causes oscillations.
And so what I can do with this slider here is I can say I want less force, I want more force. So if I say, OK, well, I was oscillating, let me try to decrease the force to make it slow down. That's not going to save us. It's still going to oscillate no matter how little or high the control force is. If we want to go really high control force, it's just going to go crazy. So now we're going to put it in a PID controller. And again, same system. We have a block that's moving. We're trying to move from 0 to 1. And let's just start off with the P. And so again, right here, you're going to see the proportional control effort show up right here. And the direction is correct, and the magnitude is correct. So however big it is to the right, it's trying to push that hard to the right, to the left. That's the same. So let's put a gain of 10. Who knows where to start? We'll start at 10. So we see a similar thing. Who knows why? Any guesses? Sure. What?
Too high?
We can try decreasing P if you like. So if we try to go, okay, we want to go slower, hit go, and it's still going to oscillate.
What does the proportional term not care about? Back to the car. The rate, right? The rate of change. So the proportional controller, it's getting the error to 0, but when it gets the error to 0, it's not accounting for the fact that the block has momentum, which is going to continue it moving. It has some speed associated with it.
OK, so we'll follow the recipe here and add a little bit of KD into the mix. So let's start there for KD. Hit go, and all of a sudden, you remember, let me hit go again. So watch that derivative control right the second I hit start. So start, see it has a big resistance to you trying to move that block quickly. And you can see right away that the block actually hits the target. And when this finishes, you'll see the nice graph there. So I would actually say it's a pretty good step response. So you moved from 0 to 1 in around a second there. It's pretty good, right? Where do you want to go next?
So yeah, so again, you still get, because of the selection of gains, you're still getting what's called a little bit of overshoot there. I don't know if you guys saw that, but it's still shot past the desired. But the difference in this case is with that derivative term, it didn't then come back and start swinging and then swing the other way and lead to this unstable or undesired oscillatory behavior. The derivative term is penalizing change. It doesn't like to see change. It only allows change when the error is large enough to justify it, and that's where this weighting comes in, and why you only see the block move when it's far away. Once it gets close to derivative terms, like we're done here.
And so then we can quickly say, OK, I want my thing to move even slower. I want this to be very slow, no overshoot, and so I'm going to add a lot more damping in there. If I hit start, you see that derivative term is fighting the proportional the whole time, such that it slows the block down. But the problem is, then you look at your step response, and it took a really long time to get to where you're trying to go to. So a lot of controls tuning, and we actually had 0 overshoot. So a lot of controls tuning is figure out, in my car, is it OK if I overshoot my target a little bit? So if you're driving in the middle lane on the highway, you want to move to the left lane. Is it OK if you overshoot and hit the sideline on the road, or do you want to be very slow and controlled about it and 0 overshoot? This is probably a safe way to drive your car, whereas the one I showed a second ago was getting a little bit, you're ripping the wheel over, laying down some rubber in the road, but you get there much faster. So that's more of an emergency kind of maneuver. And so in this system, there's no modeling error. So there's no reason why our block is not going to go to 0, or it's not going to be able to. There's no reason why our block cannot get to its reference command. So what I'm going to do really quickly is add in a spring into the system.
And just to piggyback on that, so what he's saying is, we talked about the integrated term, right? We have this to get rid of that steady state error. Was there steady state error in that plot that he showed? No, it was hitting its target. Why was it hitting its target? Because there was nothing external acting on that block that we didn't know about. Back to the car example, our foot needs to stay on the gas when we hit 70 miles an hour because we have rolling resistance, we have aerodynamic drag, we have things in the system the controller's not compensating for that mean that we have to keep our foot down. That's where the KI term comes in. So now he's added an external disturbance on the block, which will result in a steady state error.
So just to show you what's going on, so we can see that if you start the block at 1, you have the spring that's pushing the block back and forth. So that spring is always trying to return the block to the center. And so if we add damping, and if we add the D term, we can see that the block is always going to return to the center of to x equals 0 if you don't have any P or I control in there. So let's start off at 0 again and say we want to go to position 1. Oh, come on. We want to go position 1 with both some P gain and some I gain, or some D gain. Hit go. And so now you can kind of see right there, you have this proportional effort because you're not at 0. Your error is still non-zero. So you still have the proportional effort there, but you have no D and you have no I. And so this will show you exactly what the steady state error looks like. Hang on, it's almost done. There you go. So we never reached our target. So how we fix that? You see that integrator is going to be constantly seeing this error and saying, hey, I want to get rid of that error. So now if we turn on the iGain, we can let it get rid of that error. So you see that integrator kind of winds up and brings us to the target. You want to show anything else?
No, I think that's great. Are there questions on this? Also, I know Ken, we're a couple minutes over. How in trouble are we? Okay.
0.
We're going to go over to a lab and just kind of get busy. So
Okay.
as soon as we wrap up here, we'll do that.
And just to show you guys what instability looks like.
Oh, yeah, good call.
If I say, oh, I want to get to my intended target very quickly, so let's turn up the integrator really high. Let's turn everything up really high while we're at it. This isn't going to be stable, because see that integrator just winds up, and then it's still pushing. And
Maybe get rid of the D.
Yeah, I don't know if I can make this thing go unstable, actually. So there we go. So you can make your car go off and do crazy things with a controller. So at this point your car's crashed. So this is what you want to avoid.
That was perfect. Okay, are there any last questions on anything you guys learned and saw today?
Any questions? Let's go ahead.
Hey, guys.
About the last test, when you apply the scoring onto the square, onto the tube, and you apply KI, then it actually hits the target. But in reality, when we are controlling our race car, is it necessary to use KI because there won't be any force to pull the car from the wall?
Yeah, good question. So this kind of gets back into, right, okay, so in the cruise control example, it's obvious that our foot needs to stay on the gas, right, in order to stay at a fixed speed because there's drag on the car. Like, we know that from practical experience. In the case of your wall-following cars, first of all, the question is, if you end up with a steady state error, does it matter? Do you care? You probably don't in this application, but you might. The second question is, if you end up with a steady state error, why did you end up with a steady state error if there's no force exerted on the car? You end up with a steady state error because there are other things, even if it's not external forces like a spring or like aerodynamic drag. And one of them is what I was talking about, that if you command the car to go at 0 degree steering angle and you drive it straight, I guarantee the car will steer one way or the other. Yes, there'll still be deviation. And so the integrator term will get rid of that for you, if you want it to. It will help get rid of it for you anyways.
Have you ever driven a car with where the steering wheel is not exactly straight when you're driving? Yeah, my car's kind of like that. So if you can imagine if you put the steering wheel straight, you're not going to be going straight anymore, right? So the integrator would account for that, that messed up alignment you have in your front end. It's just kind of that's an example of an external disturbance in your car steering that the integrator would take care of if you cared about your exact track on the road.
Right.